As we look at section 8.3, we're going to take the third part of our logarithms and look specifically at graphs today. And to do that, we want to start off by reviewing just basic shifts in graphs using the horizontal and vertical component and also flipping over the x and or y-axis. So let's begin with a parabola. And our first one, as you can see, is a parabola because it has an x squared in it. So let's plot our vertex, which is going to be at 0, -2. And then, as you know from a parabola's pattern is 1, 1, 2, 4, 3, 9 in terms of over and up. So I go over 1, up 1 for our first point, over 2, up 4 from the vertex for our second point, and then over 3, up 9. That's going to take me off the graph for our next points. This now allows me to very quickly sketch my graph, coming down, arcing, and coming back up. So just a little review of parabolas in that pattern, 1, 1, 2, 4, 3, 9. All right, now moving over to number 2, we have a parabola again. So I'm going to label that with a P for parabola. But we have two components. We have x minus 2 on the inside. And so the factors of that x minus 2, that is going to be, it's going to move to the right 2. And then the plus 1, very simply, is going to mean it moves up 1. So that's the plus 1. So we take our normal parabola, which starts at 0, 0. We go to the right 2 and up 1. And from there, we plot our normal 1, 1, 2, 4, 3, 9. So 1, 1 on either side, 2, 4, and that takes us off the graph. And so that is the graph of our parabola, shifted over 2 to the right and up 1. Our third one, once again, is a parabola, and it goes up 2, but because it has a negative x squared, that negative x squared is going to flip over the x-axis, okay? So a couple quick notes on this problem. So let's take our parabola and let's flip it over the x-axis first, and then let's move it up 2. So we flip it over, it's going to go down that way and then up 2. From here, our pattern is normal, okay? We're going to go over 1 and down 1, over 1 and down 1, over 2, down 4, over 2, down 4. And so there's a quick look at this parabola. It is going down because it's a negative x squared. So a couple of illustrations of flipping, moving laterally up and down. Our next three, we're going to focus on exponential growth. And we're all very familiar with this, but let's review. The most important point of exponential growth is that point 0, 1. So our exponential growth is just going to slide up here and come over to there. Very straightforward. Reviewing exponential growth with a negative x, that negative x right here is going to flip across the x-axis, okay? So it's going to flip over, excuse me, I made a mistake there. It's a flip over the y-axis, so it's a sideways flip. So I'm going to mark original with a dotted line, and then I'm going to make my new graph flipping over the y-axis with a red line. So the red line is our answer here. So a negative number in front of the x flips it over the y-axis. Okay, let's look at our third one. We start with our normal growth function. Make it a dotted blue line. The negative in front of the 4 flips it over the x-axis. So it flips it across the x-axis. So I'm going to draw that in purple, coming across the x-axis. And from there, we're going to have a factor of going to the right 2. That minus 2 is right 2, and the plus 1 is up 1. So from this purple point, we go to the right 2 and up 1. Because we went up 1, our asymptote goes up 1, and so it's going to look like the purple, but it's going to go over 2 and up 1. So there we go. All right. So there's three little examples of each problem, parabolas and exponential growth. Let's now move into logarithms and other functions regarding inverses and logarithms and things like that. Here, we're going to sketch the graph of each of these, and we're going to sketch the graph first of the function itself. Then we're going to sketch the graph of y equals x, and then we're going to finally sketch the graph of the inverse of this function. So let's start off with f of x. F of x squared, we're going to make this in blue. Okay, so our f of x is a normal parabola, 1, 1, 2, 4 in each direction. So a very quick sketch of our parabola. Now we're going to sketch the line y equals x squared. So y equals x squared, we're going to have a line that's going to go slope of 1 in both directions. Okay, so there we have a slope of 1 in both directions. And now we're going to take and we're going to make our line our inverse function. And so each of our points on our original graph, 0, 0, 1, 1, 2, 4, are going to be flipped over the y-axis. It's going to be 0, 0, 1, 1, but now it's going to be 4, 2. So 1, 2, 3, 4, 2, and then obviously the symmetrical part of that. Your circle there goes a little bit above the green line and then out, and then coming down here in the same way. So the red line is our inverse function. Our green line is y equals x, and our blue line is our original function. We're going to follow that same pattern for each of our problems. 2x minus 1, starting obviously at minus 1, going up 2 over 1. So here's our 2x minus 1. That's going to be a blue line coming up here. All right, so that is our original function, f of x. Let's draw our green line. It's going to start down here, go all the way up through, and try to draw an actual line here. There we go. Making sure our slope is right on target. And now we're going to draw our red line. Now, the inverse of our points, we're going to actually plot some points here. So we have 3 points that we're going to work with to get our line. So 0, 1, 0, negative 1 is going to become negative 1, 0. 1, 1 is going to stay the same. This is 2, 3. That's going to become 3, 2. There's 3 points. That should be enough to give us our line. It has a slope, as you can see, of 1/2 going up. And now you can see our symmetrical blue and green and red lines being symmetrical on the line y equals x again. Now the red line is going to be our inverse of x. Our blue line is going to be our f of x. Now let's look at exponential growth. Once again, we go through 0, 1. 5 to the x is going to swoop up this way and come to the left. Let's draw our line y equals x again, coming up through. There we are. And now from there, we can pick a couple points if that helps you. 0, 1 becomes 1, 0. This is the point on the blue, 1, 5. So that becomes the point 5, 1. So here you can see it's going up to the right, and that's going to come down and be an asymptote on the y-axis. And so each of our color codes here, our inverse is red, our line y equals x is in green, and our original function of all of these is in blue. Now, I hope you remember from yesterday that you can write it as f of negative 1 of x, or you could also write inverse of y of these problems. Okay, our part C, we're going to look at logarithms, and we're going to graph log of 2 of log base 2 of x, and then we're going to graph log base 3 of x on the same graph. So let's start with log base 2 of x. I'm going to make this one in blue. We know a logarithm goes through the point 1, 0. And then our logarithm here is going to go over 1 and up 1 because the log of 2 base 2 is 1. So this is going to come up like about so, and then come down here. That's our log base 2. Now, Log base 3, I'm going to graph in red. And the only really difference is instead of going over 1 and up 1 from that point, it's going to go over to the value 3 and up 1. And so you notice it's a little bit shallower, and it also gets a little bit closer to the y-axis first before going down very similarly. So, summary, what do they have in common? Well, I hope you see that they have an x-intercept at the point 1, 0. And then second, do they have in common? They have a vertical asymptote. Hope you remember how to spell asymptote with a P in there. And that vertical asymptote is at x equals 0. X equals 0, remember, is the y-axis. Now, how are they different? Well, their difference, I think, can be summarized by saying the higher the base, okay, so if that number gets to 3 and to 4 and to 5, the graph is going to flatten out faster. Flatten out faster. And it's also going to get closer to the y-axis faster on the other side of our x-intercept. So with that in mind, let's sketch the graph of y equals log base 7 of x and y equals log base 10 of x. So base 7 of x, once again 1, 0, it's going to go way out to 1 up and over 7, so about to there. So it's going to be very shallow already because it's 7 of x. Now, log of base 10 of x is going to be even more shallow, still going through 0, the x-axis at 1, but now it's going to go all the way out to 10 and up 1. So this is going to be even more shallow as it goes out and makes its turn. So I hope you see just the comparison between the green and the blue, keeping shallow and then even more shallow. And up here with the 2 and the 3, these are actually very curvy, whereas our ones at the bottom are very, very angular. So just a couple comparisons. But the big picture on all 4 of these graphs is our logarithm graph, no matter what it looks like, is going to be going up to the right with a y-intercept at 1, 0. Logarithm graphs across the board, that's what they're going to look like. All right, so now let's do some shifting around. Remembering our logarithm graphs, we really don't care what the base is. They're all going to have an x-intercept at 1, 0 unless they move around. So I'm going to make my parent graph in each time just going at 1, 0. There it is in a blue dot. And now the first thing we have an x plus 1. So an x plus 1 is a shift left 1. So I'm going to go into purple here. So left 1. Our origin becomes our x-intercept, and we're going to go up like so, and then down. Our y-axis, in terms of our asymptote, has now moved over 1 unit. I'll just draw it in, and that 1 unit over goes to -1, because our asymptote, our logarithms, is vertical, not horizontal. All right, let's look at B. Normal parent function, just like all of them, a normal logarithmic function. There it is. And our dotted blue. From there, this is going to go right 2 and up 3. So going right 2, up 3. Because it went right 2, that means our asymptote, which used to be the y-axis, now is at the line x equals 2. But our shape is going to be the same as the blue dotted line, just like so. Let's look down to C. See, we have the log of 5 is our base. For some reason it cut off my G function here on the printer. I apologize for that. So that's the opposite of log base 5 of x. Well, let's start by graphing just log of 5 base x. All right, there's our basic graph. Now, if you remember, the negative out front is going to flip over the x-axis. Okay, so we flip over the x-axis. There it is, coming up, and there we have. Same point, x-intercept at 1, 0. Coming over here to D, we have the log base 4 of the opposite of x. Once again, Let's graph our parent function, if that helps you each time, of a logarithm. But because it's an opposite of x on the inside, now the flip is over the y-axis. So we're going to take this graph and we're going to flip it over the y-axis, over here to -1, 0, symmetrical to the y-axis, and there it is. On each of these graphs, I don't know if you realized it, but our axis of symmetry is just the line x equals 0, which is considered to be the y-axis. All right, looking down at E and F. E and F, we've got a unique situation that we have a movement and a flip going on. I hope you remember from our previous problem, when there's a negative out front, that's going to flip over the x-axis. So I'm going to write that, flip over the x-axis. And the -1 is going to move it right 1. But we're going to flip it first. So here's our parent function. We flip over the x-axis. So I'm going to make that into red. Here's the flip over the x-axis. I'm going to circle that because that's the flip. And then right 1 in purple from that point. So we're going to go shaped like the red graph, but our asymptote has moved 1 unit to the right. So our asymptote is the equation x equals 1. Let's look at f now. Our f function, we have our parent function just like normal. Here we go, normal logarithmic parent function. The negative x on the inside, hope you can realize that is going to be a flip over the y-axis. And then the -2 is going to be down 2 as a movement. So first let's flip it over the y-axis. So here we are flipping over the y-axis with my dotted line, being it's not the real answer. And then my final answer, taking that point, going down to same asymptote. And there we go. Our asymptote is at the vertical line, x equals 0. So I hope that's been fairly straightforward for us. For a kind of a quick summary, logarithmic graphs really are based on our parent function. And so as we look at these, we've got a lot of different possibilities that we could have, much like on the growth, but this should be fairly straightforward as we go. I've made here just a little bit of a table that you can refer to in terms of our parent function of logarithms. Remember, they're just going to be a very simple swooping up and to the right for our parent functions. And then here's all our shifts, left, right, up and down, flipping over the x-axis or over the y-axis. Might be a good summary to have as you're moving forward. I hope this has been helpful. And now we'll start our homework. Our homework will be a worksheet over much of these same ideas.